Say the word galaxy out loud, and most people picture something crossable. Huge, sure. Distant, sure. But finite. A place you could reach if you had enough time, enough fuel, enough patience. That assumption feels reasonable. It's also almost completely wrong, not because the galaxy is bigger than you think, though it is, but because past a certain point, distance behaving like distance. It starts behaving like a wall. Let's find that point. Start small. On the clearest, darkest night you will ever experience, the human eye can pick out somewhere around 2,000 to 3,000 individual stars. It feels like a lot. It feels like most of what's up there. It is not. The galaxy contains an estimated 100 to 400 billion stars. What you are looking at, on the best night of your life, is a rounding error, a sliver too small to register as a fraction. The rest is not missing. It's just too far, too dim, or hidden behind lanes of dust so thick that even our best telescopes cannot see through them. This is where the first crack in the intuition shows up, because far implies a number you could eventually count to. What we are actually dealing with does not work that way. The Milky Way is somewhere between 100,000 and 200,000 light years across. A single light year is already close to 6 trillion miles. So, before you even start moving, you are not measuring a big number. You are measuring a number made of numbers. Here's a way to feel it instead of just hearing it. Shrink the entire galaxy down to the size of a running track. 400 meters, one lap. At that scale, the sun, the Earth, every planet, every probe humanity has ever launched would compress into something smaller than a single grain of dust on that track. Not small, not visible under a lens, gone, below the point where the model can even represent it. And we are not floating somewhere quiet inside that structure. We are on the move. The entire solar system is currently orbiting the galactic center at roughly 514,000 miles per hour. Carried, not chosen. At that speed, one full lap around the core takes about 230 million years. Human civilization is roughly 10,000 years old. We have never come close to completing a single orbit of our own galaxy. That's the neighborhood. Now try to leave it. Let's be generous. Let's take the fastest machine humanity has ever built and point it straight across. Voyager 1 has been flying since 1977, and it's still the farthest human-made object from Earth. Its cruising speed, about 38,000 miles per hour. At that pace, crossing the Milky Way from one side to the other would take somewhere between 1.7 and 3.5 billion years, depending on which edge of the disk you are measuring to, not a typo. Billion with a B, either way. So forget Voyager. Let's go to the actual speed record. During its final close passes by the Sun, the Parker Solar Probe used the Sun's own gravity as a slingshot and reached roughly 430 visozen miles per hour, the fastest anything built by human hands has ever traveled. At that speed, non-stop, no delays, no failures, crossing the galaxy would take somewhere between 150 and 300 million years, depending on exactly where you decide the disk ends. For context, 150 million years ago, the supercontinent Pangaea was still tearing itself apart. Whatever we built to make this trip would still be traveling long after every landmass on Earth had rearranged itself into shapes we wouldn't recognize. And here's the part that quietly ruins the achievement. Parker only hit that speed because it was falling toward the sun, borrowing the sun's gravity for free. In open interstellar space, there's nothing to fall toward. No slingshot, no shortcut. Whatever speed you launch with is the speed you are stuck with, unless you burn fuel to go faster, which means carrying more mass, which means needing more fuel to move that mass. The number does not just stay bad. It gets worse the more you try to fix it. Our best technology, aimed as generously as physics allows, is not just insufficient. It is not in the conversation. So, there's one option left. Push toward the actual speed limit of the universe. Nothing with mass can reach the speed of light. Not because we have not engineered our way there yet, because the energy required to get a single kilogram of matter to that speed is infinite, not extremely large, infinite. That's not a technology gap. That's the universe declining to negotiate, but we can get close. Suppose a ship reaches 999% of light speed, 5 nines. As far as we are going to push this seriously, something strange happens here, and for a moment it looks like a way out. Einstein's relativity says time does not pass at the same rate for everyone. It depends on how fast you are moving, relative to something else. This is not theoretical. It's been measured directly, with atomic clocks flown on airplanes ticking a fraction slower than identical clocks left on the ground. At 99.999% of light speed, the math works out to a factor of roughly 224. For every 224 years that pass back on Earth, the crew on board experiences about 1 year. Apply that across a 100,000 light-year crossing, and the trip that takes Earth roughly 100,000 years takes the crew somewhere around 450 years. 450 years, not 100,000. That's the flip side of relativity. 2. From the ship's own frame, the galaxy physically compresses in the direction of travel. Distance is not just crossed faster, it's reshaped by the act of moving through it. For a moment, that looks like the answer. It is not, because reaching 5 nines of light speed means accelerating continuously. And as a ship's velocity climbs toward that limit, its effective mass climbs with it. The closer you get to the ceiling, the more energy every additional fraction of a percent costs. Not in a straight line, but on a curve that goes nearly vertical near the top. The fuel required, using anything resembling known energy storage, does not exist. It's not a matter of budget. It's a matter of the number being larger than anything we could physically carry. And even if that problem had an answer, the trip itself would still try to kill everyone on board. Interstellar space looks empty. It is not. It's full of stray gas, dust, and the occasional lonely atom. At normal speeds, that's irrelevant. A spacecraft passes through it like a car through fog. At 99.999% of light speed, that same environment turns lethal. A single hydrogen atom striking the hull carries the impact energy of a fired bullet. Not occasionally, continuously for the entire crossing. A particle the size of a grain of sand hits with enough force to be structurally catastrophic. The obvious answer is shielding. Thicker walls, denser hulls, except shielding has mass, and mass is exactly what makes reaching that speed impossible in the first place. Every gram of protection you add is a gram the engines have to fight against, at a cost that was already climbing toward vertical. Protecting the ship and accelerating the ship are now working directly against each other. There's a second version of the same problem coming from the front. At near light speed, starlight ahead of the ship gets compressed by the ship's own motion, shifted up in energy from visible light into ultraviolet, then X-rays, then gamma rays. The front of the vessel would face radiation lethal to an unshielded crew within minutes, generated simply by moving fast enough toward the stars ahead of it. So, the plan that looked like a loophole has turned into 3 compounding problems that all make each other worse. And we still have not reached the part that actually breaks the mission. Assume somehow the ship survives all of it. The fuel curve, the radiation, the particle strikes. 450 years is still more than a dozen human generations. Nobody who boards this ship sees where it's going. Everyone alive at departure dies in transit. Everyone who arrives, if anyone does, was born inside a hull, raised inside a hull, and has never once stood on solid ground. Here's where the isolation becomes total. Right now, a radio signal from Voyager 1 takes about 23 hours to reach Earth. Already a strange kind of distant. On a ship traveling at nearly the speed of light, moving away in roughly the same direction it's transmitting, a message sent home would not get a reply for tens of thousands of years. There is no mission control. There is no course correction from the ground. There is no version of phone home that functions on any time scale a person could wait for. From an early point in the journey, whoever is on that ship is entirely, permanently on their own, solving every failure with whatever happens to be on board, because nothing else will ever arrive in time to help. And there's a threshold buried in all of this that almost never gets discussed because it doesn't announce itself. At some point in the acceleration, earlier than most people assume, the fuel required to slow down, turn around, and return to Earth exceeds anything the ship could possibly carry. Past that point, the decision to keep going is not really a decision anymore. It's just what's left. Nobody rings a bell. There's no ceremony. The ship crosses a line it cannot see, and turning back stops being a choice and becomes a physical impossibility. Meanwhile, back on Earth, hundreds of thousands of years are passing during those same 450 ship years. Everyone who watched the launch is gone within decades. The nation, language, and culture that funded the mission are gone within centuries. On the timescale the ship needs just to cross one galaxy, entire civilizations could rise, plateau, and vanish more than once before the journey is even a third finished. So, if a ship somehow endured all of it and reached the far side, what would actually be arriving? Not the crew that left. None of them would still be alive. Not a mission with living authors. Everyone who designed it, funded it, and understood its purpose would be, from any reasonable frame of reference, hundreds of thousands of years dead. Whatever culture exists on board, after 10+ generations of total isolation, would have drifted from the original in ways no one could fully predict. No outside contact, no correction, nothing but whatever the last generation managed to pass down intact. And that's the part worth sitting with. The question we started with: how long would it take to cross the Milky Way? Assumes there's a you that leaves and a you that arrives, connected by a single continuous thread. It assumes home is a fixed point, waiting on the other end of a return trip if you ever needed one. Neither of those things survives the scale we're talking about. The travelers who leave are not the ones who would arrive. The Earth that launches the mission is not the Earth that exists, if it exists at all, by the time the ship reaches wherever it's going. Somewhere in that gap between departure and arrival, crossing stops being a single event experienced by anyone in particular. It becomes something that happens across generations, across civilizations, without a single mind present for the whole of it. Maybe the real answer was never a number of years. Maybe the question itself assumes a kind of continuity that physics never promised us. And the true size of the Milky Way isn't measured in light years at all. It's measured in how much of us survives long enough to find out.